No. No. All right, folks, welcome again to our Wednesday evening paper reading. The topic of today is a very influential paper. It is called CAN, Kolmogorov-Arnold Networks. This paper has had sort of I'm surprised at the level of controversy it has generated. Some people have trashed it by saying it's nothing but learnable activation functions, and you'll see why. And other people have called it to be exaggerated, or perhaps gone hyperbolic, praising it as saying this is one of the biggest breakthroughs that will completely replace MLP. So while there are these extreme points of view, let us take some time to carefully walk through this paper and see what is its real contribution. And of course, when I say real contribution, it's a little bit subjective, a little bit about myself. One of the authors here, Arnold, or V.I. Arnold, I learned my chaos theory and nonlinear dynamics. Actually, he has a classic written in physics, which is literally mathematical methods of classical mechanics. And Kolmogorov-Arnold are, of course, great mathematicians, amongst other things. Their work on KM theorem and so on and so forth, foundational to chaos theory and dearly loved by physicists. So it was a pleasure, actually, to read this paper. And I found the paper very insightful. Whether or not it will prove to be of significant practical utility, time will tell. But there is no doubt in my mind that this paper represents quite a milestone. And it is very beautifully argued in terms of the thoughts that it represents. It's surprising how, with very clear articulation of a different argument, you can create an entirely different kind of neural network. And so we will deal with that. Now, the areas that I would put emphasis on from my perspective is, which is not as much talked about, it is the interpretability of neural networks. One of the big problems we have with deep neural networks is they are hard to interpret. We use all sorts of surrogate models to try and post hoc impose interpretability over them. It has always been a struggle. And I believe that this paper is a significant contribution to understanding the relationship that the machine has found in making prediction. How is it representing specifically as symbolic functions, as we know it? Y is some function of x, where x is a n-dimensional vector or d-dimensional vector. So what is the nature of that function? If you ask a neural network, the neural network typically would shrug and say, I don't know, but I can make perfectly good predictions for you. Right? And that has been the most frustrating sort of an issue from an interpretability perspective. And this paper, I wouldn't say that it solves the problem, but it certainly shows a potential avenue to make progress in that direction. And that is interesting. The other reason that I found this paper interesting is, suppose you do not know the dynamics. These functions represent relationships of physical forces, for example. If you do not know the specific equations governing the relationship, it turns out that KN networks, as opposed to multilayer perceptron, they give you an insight on what could be a good symbolic relationship, a good equation between the input and the output. And they give quite a few examples showing that it essentially rediscovers mathematical and physical laws. It discovers physical laws quite well, and it also discovers interesting results in mathematical knot theory. So what is a knot? A knot is basically, think of it as a loop in 3 dimensions, and its deformation, various deformations of the loop, right? When you tie your shoelace, that is not a loop, actually. That is not a knot, actually. Though we call it a knot or a double knot, in reality, mathematicians would call it an unknot, because you pull at the ends and it unknots itself. So in their case, a knot is something that truly is a knot. You can't unknot it by pulling or deforming it. Right? So just a very little bit about knot theory. But so it's a very fascinating field, and you would wonder, why are mathematicians obsessed with knots? Don't they have something better to play with? And it turns out that knot theory is at the foundation of a lot of beautiful things, including results in theoretical physics and understanding the foundations of nature. So the impact that it has on physical sciences or scientific exploration, I believe, is far more promising. People have argued on the internet that is it better or worse than MLP? My own personal feeling is that question is besides the point, right? Whether it will, like, for example, perform better, whether it will do or not. For me, the big contribution is it becomes a tool for a mathematical or a scientific co-discovery, and it helps you in getting some level of interpretability or intuition or sort of into the dynamics of input and output. What's the relationship between the two? And that is a perspective that will inform my reading of this paper. So with that, this paper needs some mathematical foundations to understand. One is that it replaces the basic neuron of the perceptron. It replaces it entirely. On the one hand, it simplifies the node and it brings in something else. It makes the edges into functions, which is odd when we are, and so I'll talk a little bit about that. And this paper needs two mathematical backgrounds, both of which I'll build upon. And I think both are essential. If you get those two things, then it becomes a fairly easy to understand the core intuition behind this paper. So we think of a neuron as this. Let's say that, let's take two variables, and I'll just take two variables throughout this paper. So we have this. We say Z is equal to W1, W2, and a bias term. And we would say that it is B plus X1, W1 plus X2, W2. Right? So these weights are scalars. And this is a core thing that this paper talks about quite a bit, that at the end of the day, these things are W1, W2, B. These are scalars. Or more specifically, Wi and B, they're just some floating point number, isn't it? When you download a model, what you're downloading is a giant file with a lot of weights and biases, right? Matrices of weights and biases. This is it. On the other hand, inside the node, so edges have weights, but this is therefore a linear transformation. And this is, of course, the classical neuron. And this is the activation function. And you typically pick an activation function. You may pick sigmoid. Like, for example, there could be a logistic function. It could be tanh. It could be the error function, and so on and so forth. Sigmoids have a whole family of shapes that you could go with, or you could go with shapes that are broadly like this. Like you could have ReLU, GILU, SILU, and so on and so forth. There's a whole long list of things that roughly are rectified, sort of, I'll use the word rectified, very much like a diode in a electronic diode, means signals propagate, positive signals go through, negative signals are essentially, in the negative regime, it is approximately equal to zero. Right? This is the nature of the other class of activation functions that are popular in neural networks. Right? Now, what this paper will argue, quite interestingly, is it will turn this thing on its head. It will say these activation functions are complex. They introduce nonlinearity. Right? So in a way, you can say that the signal comes into the node First, it goes through a linear transform, and then it goes through a nonlinear transform. And a multi-layer perceptron or a feed-forward network or any one of its synonyms, they are sequences of linear and nonlinear transformation. In a way, all deep neural networks, even with attentions and everything, they are sequences or alternating sequences of linear and nonlinear transformations. Linear transformations followed by some activation, followed by again set of linear transformations, followed by activation. And it sort of goes on. That's how you build deep nets. Now, what this paper will argue, and I'll just redraw the picture again, just for clarity. We have Z and we have the activation. This is the node. These were your weights, X1, X2, X1, weight 1, weight 2. These are your inputs. What it will do is, it will, for reasons that will become clear, it will actually turn the whole thing on its head, and it will say, we don't want the function here, the activation function here, because if you put activation function, it comes after the linear transform, right? We want to change the order of the two. So if you change the order of the two, it is almost like you have activation function. This goes here and this goes here, sort of, right? But this not only goes here, what you do is you put it here and here, the activation functions. You put it on the edge. And then because you have the flexibility to, you actually change them to different activation functions. And they don't use the word sigma, they use the word phi in the paper, but I'll just use the word sigma. So you can actually have two different activation functions. And here is the trick. They also say that these activation functions need not be your ReLU, GILU, CILU, or your tanh sigmoid. It can actually be any function, any smooth function, smooth differentiable function. Right? Smooth, obviously, geometrically, smooth and differentiable are synonyms. The smooth curves are differentiable, differentiable curves are smooth, manifolds are smooth, right? So just put it as like that. Now, why would they do that? And what is the basis for doing something like this? Why would you turn the tables upside down and look at it like this? That is the gist of this paper. So what it says is, let me just put it this way. What it's saying is that when you have X1, X2, it will go through some function. So we use sigma 1, but I'll try to now align with the notation of this. Some function phi 1, and this goes to some function, let's say phi 2. And these, now you notice that these activations are on the edges themselves. They then feed into the node, but all the node has remaining now is Z, the linear transform. And it trivializes the linear transform to just the addition. So let's say from this comes out phi 1 of X1, and this is phi 2 of X2, some function of X2. So this is nothing but a linear sum of this. Right? So I will just make it a little bit real because it's saying something pretty startling. Let us say that these are two dimensions of your data, X1, X2. So you realize, let us say that this is, for example, I will take an example. Let us say that phi 1 is equal to X square and phi 2. I mean, what phi 1 does, let's say phi 1 does, take X2, X square. And so phi 2 also does this, X2. Let me just say X, I don't know, X square also while you're at it. Right? So they're basically the same phi. So I could just have said phi 1 and 2 are both doing the same thing. Whatever input you give, it will square it. So then if you look at Z, it is just X1 square plus X2 square. Right? Now, what does Z represent? Z represents a surface. It represents something in a two-dimensional space. And one of the interesting thing it says that once you get Z, you can further deform it. You can apply another function on it and bend it and do all sorts of things to it, right? So you will take this and you can bend it somewhat, right? Squish it a little bit. That will be another function. In this paper, phi's get mixed up. So for the sake of simplicity, I'll call it as a phi function of Z, another function, another deformation of Z. So you say, oh, all right. Now this begins to look rather complicated. And what you can do is you cannot have just one deformation. You can have multiple different functions and different deformations. So you have a lot of flexibility. You can, and this will become more clear as we talk. This is saying that you can create this kind of networks in which you have activations on the edges, and the nodes are very simple, just linear addition. The activations, do you notice that if it is on the edge, it has a pretty interesting implication. It can only be the function of one variable, whatever variable is coming in, isn't it? And what it is saying is that, you know what, our basic unit now, the neuron that we're making, one neuron, the new kind of neuron we are making, is made up of univariate functions of single variable, plus just additions of different variables. The only function that we allow across variables, let's say temperature and pressure, is just addition of those two, right? A phi1 and phi2. You can just add them. And you say, well, will that be sufficiently rich if you were to build things like this? And of course, z gets fed into a pi function after that, which brings its own deformations. Will it be sufficiently rich or expressive to capture the shape of every possible function? Because at the end of it, when we start with the standard feed-forward network, the neuron, we have the guarantee from a theorem, and that, let me introduce the first part, universal approximation theorem. Approximation theorem. Most of you may be familiar with it, but what am I doing? Theorem, which basically says that y as a function of x, no matter how complicated the underlying relationship surface is, the manifold is, you're guaranteed that just one layer neural net will be able to understand this. Okay, guys, this is freezing on me. I apologize. Today I'm having a sort of technical difficulties. But just give me a moment. Okay. And am I able to scroll down? No. Okay. I'm going to close OneNote and start it again. I apologize for the technical difficulty. But what we say, the universal approximation theorem says that you can create a single layer neural net, so long as it is sufficiently wide, it can approximate any function in the world. Right? However convoluted, however high dimensional it is, it will be able to approximate it. So that our belief that neural networks can solve most problems or any problem ultimately is rooted in this mathematical result. It's a guarantee, right? What it doesn't guarantee is how efficiently it will find the solution. You may have to train a very, very long time. Now, the second stage that comes is we realize that having one layer and training with one layer is actually inefficient. Right? You're far better creating deep layers, right? Layer after layer. The same thing can learn much better rather than creating, on the other hand, one ginormous layer, which the universal approximation theorem will guarantee will solve the problem. Just instead have layer after layer after layer. And then you will notice, if you have experimented with this, which most of you would have, that this network learns faster. Are we together? And so because of the universal approximation theorem and the fact that well-behaved activation functions, anything that you build out of neurons with a bias term, weight j, like, you're guaranteed that any network that you compose out of this will solve your problem, right? And it has been the workhorse of our world for a very, very long time. But it comes with certain price. The price that we pay for the traditional, especially in the world of large language models, are, first of all,
So to get kind of like another intuition on this, like in a geometric space exit, for like a traditional like MLP, like for each of the neurons, essentially like you would be reorienting like a plane and then maybe like, you know, exaggerating it in a particular direction.
With the affine,
And
that's
then,
that's the linear transformation,
yeah,
and then the sigmoid is the
and then
deformation.
you
Is the So that is what it is. Yes, very much so. So, and that is why we say that it's a linear and a deformation. Linear is just rotation and stretching, and translation, and the bias term translates it, and then the deformation, which can be non-linear.
and then
So-
But in an MLP, the nonlinearity is chosen ahead of time, whereas in a Kahn network, those are learnable functions.
Yeah, very much so, very much so. So you guys obviously have read the paper. It's very, very true. Finish your thought.
Oh, no, yeah, I was gonna say for a conlink, also the definition might be more complex than the
That is
definition
right.
of
That is
conlink.
right. So hold that thought because many have not read the paper. So, so guys, this and as one of you, Andrew, you pointed out, in this you start with a hardwired activation. Make your choice. It becomes your prior, right? And it has its own inductive bias. For example, if you choose ReLU, very hard ReLUs. So what will happen? Any function that you approximate will look, I mean, I'm exaggerating it, will look like this. Right? And I'm obviously exaggerating the piecewise components of the ReLU. So it induces a certain structure on the function that approximates your data. Right? And that is one issue with that. The other issue, and again, the reason we say that begs the question that, but there's recent research that says we can make learnable activation function. But even when you take learnable activation function, and there's a whole class of work, but in the simplest form, all people are saying is, let us have one global activation function for the network, or at least one entire layer, and let's learn its structure. Right? Using either, let's have a polynomial representation or some basis expansion and just learn its structure. Right? That's what you're saying. But just have one global thing. And then there are variants of it. But there has been some work, obviously, in that direction. Now, the other aspect with feed-forward networks is, if you look at, for example, a transformer, a large language model, you will see that the vast majority of parameters, the vast majority of things, they go in these dense layers, feed-forward layers. So what you have is, you will have your transformer attention heads, right, which will do your KQVs, transforms. You will get the attention vectors, and then you will go through a few feed-forward layers, feed-forward network. The trouble with feed-forward network is everything is connected in one layer, is connected to everything else in the subsequent layer. Every node is connected to every other node. So the number of edges, so suppose this layer has, let's just take 1024, and this layer also has 1024 nodes, or 512, or pick your number. What you're looking at, it is a quadratic problem, 1024 squared, and already you're looking at 1,000,000. Right? Just right there, you have 1,000,000 parameters. So most of the parameters are sitting there in your dense or your feed-forward layers. Now, one interesting observation about feed-forward layer is they have this problem that if you change any of the weights locally or at any location, then it can have fairly global implications. It can affect many, many things downstream. The whole structure of the prediction and everything can change. The shape of the function can change. And you can do little experiments to see that it happens. So one of the reasons this is implicated is, and this is, people are conjecturing, that maybe that is the reason that feed-forward networks have the problem of catastrophic forgetting. So, you know, many of you, when you try to take your transformers or your large language models, the question is, should we RAG it? Should we fine-tune it? Should we just do good prompting? I mean, see, good prompts in context learning versus fine-tuning. It's always a debate, right? Generally, many things can be achieved with prompting. If you get away with it, it's great. But when you don't get away with it, you get into the fine-tuning business. But fine-tuning has proved to be the dark arts, right? So you do it a little bit carelessly, and you will induce catastrophic forgetting, right? Or put more mathematically, if your data distribution, the new data distribution with which you're fine-tuning a model, departs significantly from the distribution, the probability distribution over the original data set with which the machine was trained, essentially the machine is saying, aha, what I know departs significantly from the new reality. Let me learn the new reality. But in learning the new reality, it is not an additive process. It's a destructive process. It says, that is the new reality. Let me move towards that and let me abandon what I know, in effect. Right? So it leads to catastrophic forgetting. It's one of the issues. And this paper actually, one of the thoughts that arises in this paper is, can it potentially avoid the problem of catastrophic forgetting? Right? So those are the two things to keep in mind. But we will leave our understanding of feed-forward networks at this stage, and we'll take a digression into two sort of background topics. One of them is something called splines. Those of you coming from computer vision, anybody very familiar with splines? Theory of splines?
Yeah, I come from computer graphics, so I understand the NURBS, the weights and spans and all these functions. Yes.
Yes. Okay, wonderful. So we'll talk about splines first, and then we'll talk about these mathematicians, the great mathematicians, Arnold and Kolmogorov, and what they have to say in this context, in a slightly different context. So splines are very interesting. The origin is like this. You take a very thin piece of wood, right? And for example, in shipbuilding, suppose you take a piece of sliver of wood, right, which is flexible. You can bend. Like, imagine that you have cut through a tiny sheet of plywood, and now it's a tiny thin sheet of plywood. It's flexible. It can flex. What you do is you take this. You just say that there are these things called control points that you put. At those points, you put these little hooks on them, and with the hooks, you put something. And by the way, I learned this history from a very interesting YouTube video. You put something that looks like a whale, but if you look from the side, it looks like the head of a duck. Right? Well, it doesn't quite look like the head of a duck to me, but those people believed in that time that it looked like the head of a duck somehow. So that's why these are called duck weights. And what you do is, with the duck weight will have a hook, and this will have a hook. Let's say another duck weight is here. It has a hook, and this duck weight has a hook. And now what you do is, this duck weight, let us say, pulls it this way. This duck weight pulls it this far, and this duck weight pulls it this far. Because this wood is flexible, what it will do is it will change its shape. It will now take the shape. Let's try a different color, this color, and a fat one, let's say. Would you agree that it will look something like this, a smooth curve like this, right? Now, one of the interesting things about this curve is, and here is the physics intuition of spline. Oh, you see, you're bending a flexible thing, right? When you bend it, you will surely end up with a curve which minimizes the curvature energy of the bend, right? It will not, it will obviously, because you're pulling on it, right? So this particular shape is the basic intuition of a spline. It will be smooth, right? And so let us give some properties of it. And by the way, when I speak of this, the splines comes in many shapes and varieties. And I will sort of be a little bit barbaric, and to oversimplify, I'll club them into just one definition of a spline. Right? Those things are called the C1, C0, C1, C2 continuity. What it means is C0 continuity just means you didn't break that piece of wood, right? Or metal or material. You didn't break it, right? Yet. You can't break it. So that is C0 continuity. It's just a continuous shape. A C1 continuity just means that at any point, like at this point, these are called control points, or knots. The tangents coming from this side is the same as tangent going forward, right? The tangents are continuous. You see the tangents keep changing, the slopes keep changing. So the slopes are slowly changing. You don't have, like, for example, if I have this, you see slope here is this, and it suddenly rotates to this. right? If I had a peak. So that would not be C1 continuous. So continuous slope is also continuous. Slope changes continuously. And this is curvature. Effectively, think of it as curvature is the second derivative, right? So if this were a function, the second derivative of the function, dx square, right? That also goes smoothly. So now here is a simple intuition that I carry. Imagine that this is you're driving along a road. You would want your road to be unbroken, right? You wouldn't want gaps in the road. So that's your C0 continuity, right? C1 is your speed shouldn't suddenly have abrupt changes, right? It shouldn't suddenly, for example, the only way it could have abrupt changes is if you hit a wall, a rock or a hill or something like that. Shouldn't have that. It should be smoothly moving. And likewise, your acceleration, your foot on the acceleration goes up and down in a rhythmic manner. Right? It doesn't suddenly change, right? That's what it is.
Another physics-based intuition is like the space-time continuum.
That also has that, yeah. So this particular curve, now here is the one thing to know about this curve. The second derivative always measures, in a way, is a measure of the curvature. And the energy that is here is square of this. It's basically, when you take this curvature, out of this you can create effectively with some formula, the bending energy of this particular curve. So splines are things that try to minimize that. Right? If you try, now the whole comes the mechanics of figuring out the spline, and there are lots of tricks, and there's a whole thinking around it, and spline is a topic in its own right. The most popular of them is something called the natural cubic spline. What a natural cubic spline is, it basically tries to approximate sections of the spline, certain sections of the spline, with basically 2 bends at most, right? So it will say, let's say this. Are we together? So now it will say that if I'm going to join this point, I'm going to join these points with no more than, let us say, 2 bends. So these are cubic. Natural simply means C1, C2, C3 continuity. C0, C1, C2 continuity. Like it's a smooth, nice curve. It has a very simple, like if you do computer vision, it has a very interesting implication actually. These surfaces, which are natural cubic splines in 2 dimensions, if you look at the reflection of things, there will not be a jarring discontinuity, right? They will look like the object that they look deformed, but they will have a continuity there throughout the surface. Right? So those are natural cubic splines. Then comes the concept of, well, that's one spline. Then comes the concept of something called Bezier curves, right? So this is a quick journey. There's a Bezier curves. And computer vision people know it, but I'll just give you an intuition. So suppose I tell you here, and this point, I tell you the location. I tell you that the slope here should be this much. This is the slope. This is the point x1, and I give you that df, dx. You should be going up in this with this speed, and here you should be going down with this speed, df, dx at x2. Should be this, right? This is x2. Then what you do is you say, okay, let's join it with a curve. So now you have 2 points and 2 slopes. The trick is quite interesting actually that they figure out. What you say is, let's first of all go in the end, opposite direction of the slope. Yeah. Pretend as though you reflected it. So this is the negative f prime at the slope, right? And what you do is you take this distance, x1 to x2. This is x2, let's say, x2. You break it in 1/3, 1/3. And you ask yourself, this meets here, and this meets, let's say, this meets, in this particular case, or maybe this one was downward sloping, I don't know. This one was downward sloping and it met here, but it doesn't matter. It goes here and this goes here. And you basically join these 4 points. And you basically say, you need a shape. These are the control points. You need a shape that is completely within the convex hull of this thing, right? These are Bezier curves. That is sort of smooth curve that is pulled by all the control points, right? But is inside the convex hull. So there's a long theory of Bezier curves. These are very beautiful things. I would strongly encourage you to watch videos on Bezier curves. That brings us finally to one last mathematical thing that this paper uses, which is B-spline. Now, what are B-splines? What it says is, suppose I tell you that you must have data going through all these things. Take sets of 4 points, join them, join them, join them. I hope I get my construction right. Right. Let me get that construction right. So what you do is you again do the 1/3, 1/3, 1/3 bisection. Why 1/3? Because that's a convention. That's what you tend to take in this situation. So if I do 1/3, 1/3, and 1/3, now I can join these two. Right? Is that true? And I can join these two. Sorry, these two. Right? And then you take the midpoint of this and midpoint of this. It's a very interesting construction. And you take likewise this to this. What would I do here? These 4 points, 1, 2, 2, 3, 3. Okay, so you try to build a Bezier curve that, and this one you join to what? To this, I think 1/3 something. Okay, there is a way. I'm getting the thing wrong, somewhat misguided. But you build a Bezier point. First, you find control points. You know, things that will pull at by doing 1/3, 1/3. This breakup, and there's sort of a mechanics of doing that. And when you do that, you establish your control points, and then with the control points, you build a Bezier curve. And then you keep on going to the next 4, next 4, next 4, and what you end up with is a very smooth curve. A beautiful curve that interpolates, B-splines interpolates between the data points. Now, it is often used for nonlinear regression. People have used it to fit nonlinear regression curves to data. Are we together? Right? So that's a notion of B-splines. And it takes a little bit of a review. Every time you look at it, it's pretty straightforward. It comes to you, and then you again sort of, okay, what was it that, where are the points, control points to be placed? You get that. Now, B-splines have a property which natural cubic curves don't have. The property they have is, if I were to move 1 point away, if I were to make local changes, the entire shape of the spline doesn't change. The change stays local. Are we together? So suppose I have a B-spline that is like this. And suppose this one is being pulled by this data point, right? If I move this data point here, what will happen is the changes will be only local. Do you notice that the changes are local? You don't have changes far off. If you were playing with just natural cubic natural splines, then changes are much more, they can lead to non-local changes. Right, which makes the B-splines quite a favorite amongst people who do design, surface design, and computer vision, and so on and so forth. Right.
Question.
Other natural cubic. Yeah, please go ahead.
So do the B-splines actually ever go through the points, or they're only because you use the word interpolate? They don't necessarily go through the points of the control points that you're drawing.
They don't guarantee to go through the control points. In fact, most situations, they sort of go in the proximity of it, but never through them. Because they're always opposite forces at play. Right? So you realize that B-splines, therefore, are a departure from the traditional mechanical wooden splines, right? In which you literally pulled with the duck weights. So today, B-splines are a workhorse of many fields in which they are used. But the one property that we will sort of fixate on is that local changes can be local. If you move only some data points, it doesn't affect the entire shape of the B-spline. The impact is local. Right? That's important. So impact is local. Yeah. So that makes B-spline somewhat of a favorite for many people, including the authors here. That is one. Now comes another mathematical fact which you'll use in the paper, which is literally the Ka representation theorem. And it is also called the function decomposition theorem. It's one of those most remarkable theoretical results that most people have not heard of, right? Unfortunately, but it's a beautiful insight. What it says is something quite startling. It is so startling that you will have difficulty believing it. It says that any multivariate function, right, that you can think of anything you want. And I thought I brought some examples, but I seem to have not done it. But okay, I'll try to cook up some examples on the spot. So suppose you take a function like sine x plus y. This is, you know, that if you were to expand it out, it would be what? Sine x cosine y plus cosine x sine y, right? So let me say that sine x cosine y plus, I hope I get my trigonometry right, cosine x sine y. Am I getting it right? I think so. Let's say y is this. Right? First of all, this can be reduced to this. Right? You happen to know that it can be done. There's some trigonometric identity that can do this. And now comes an important fact. If I say that when you have a function of two variables, the only operation you can do is add. Plus is the only thing or operator across variables. You cannot do anything that is not across variables, and then any function can be represented as a sort of a two-layered function, right? Like, for example, you can say x plus y is, this function is just fx is equal to just x. If I take this function and y remains y, so inside there is x plus y, and then after this function, so this is your inner function, z is equal to x plus y. It is the only part in which two variables are being added. You're not allowed to square them. You're not allowed to do anything with them. You can just add them, right? These functions. Actually, these are functions. So even though these are identity functions, I will call them fx and some g of y. Take some function of x, some function of y, plus g of y, and then you produce a z. We can do that. In this particular case, it is just x plus y. And it says that your function can be represented as some other function, let me call pi of z. Right? Here, pi of z is just sine of z. Well, this is a trivial example, right? You can easily map it. So if you map this to fx, y is equal to sine x plus y, you know what is f? F is just identity function. What is g? G is also identity function, right? And what is pi? What is the function pi? The sine, right? Now you say that, well, what is the big deal about this? Right? This we could do, but now let's look at something a little bit more complicated. What about x times y? Now clearly there's a multiplication. How in the world are we going to convert this into an addition? If the only interaction between two variables is addition, now it's problematic, isn't it? Till you think a little bit and you say, well, you know what? There is some mischief we can do. We can say x plus y square plus x minus y square, right? Or sorry, minus, let me just say. And then I suppose, what would it be? Maybe the outer function, then 1/4. Now, do you notice that the product of x and y has disappeared? Right? You say, okay, well, let's try something harder. Maybe multiplication was too easy, right? How about x divided by y? Right. Well, what about this? Log of x minus log of y e to the. Now, have we again reduced it to just simple addition, subtraction of, right? So, or rather, yeah. So you guys are getting the idea, right? How this game can be played, isn't it? So now, building on this thought comes a very powerful result. The powerful result is a result that is called, which is written in a very abstract form. So, and I will try to unpack it and make it unabstract, hopefully. It is this result. It is, and I suppose because it's written like this, most people look at this wonderful and most remarkable result, which says that this game that we played with xy, and for simple functions, you're guaranteed to always work for any multivariate function. So just think about it for a moment. The Kolmogorov-Arnold representation theorem is one of those most profound statements that is saying that no matter how complicated a function is of arbitrary many variables or arbitrary many dimensions, it can be decomposed into univariate functions, which at most can be added, right? Additively. So there is a two levels of addition, the inner layer and the outer layer. Right? You add and then you apply another deformation function on it, right? So this result is quite startling. The fact that you can do it, this little game that we played with just a few examples, it might not have occurred to you that a product can be converted into additions of variables.
That's my question, actually. Like, is it mathematically
guaranteed?
Guaranteed.
It's guaranteed. It's a theorem. So the good thing about theorem, unlike product development, is when the first release comes out, it barely works. Right? Second release might work. Right? And unlike that, mathematics, once a theorem is proven, once and for all eternity is proven. There's never been a V2 of Pythagoras theorem.
Yes.
Right. So and it comes with absolute guarantees, money back guarantee. Right. So Pythagoras, so just like that, this Kolmogorov-Arnold theorem is a theorem. You can't argue with it anymore.
Yeah, it's kind of like a generic function extending any curve can be represented as summation of sine curves.
That's right. It's a basis function in terms of basis function. And in a way, it is along the same line, except that it's not using, the remarkable thing is it's not using basis function. It is saying that this decomposition will always be true, univariate, and the only operator is summation. Right? Now, that is a very startling result. It begs the question, well, how would you find that out? Like in this case, we had some clever, like these examples look simple, and we sort of figured it out, right? With a little bit of thinking, we figured it out. And for very complicated mathematical functions, how will we do that? And that's where a bit of the bad news is. Kolmogorov-Arnold theorem says, well, figure it out on your own. In other words, it doesn't give you a constructive process. The proof is not constructive. That shows you this is the way you can go about finding it.
Is that theorem in a different paper or the same paper?
No, Kolmogorov-Arnold theorem has been there for a very long time.
It's an approximation theorem.
Yeah, it is there in functional analysis for a long time. Right?
It's references 5 and 6 in the paper.
Yes, yeah. Like I mentioned, right? Arnold has done many things. I got my chaos theory and nonlinear dynamics foundations from Arnold's classic book. Yeah. So these guys are great mathematicians. By now they must be very old, because when I was young, in my early 20s, I read from Arnold's textbook, which means Arnold must have been in his 40s or so. So by now he must be late 70s. Anybody wants to find out how old they are? So anyway.
I thought he died.
He died, is it?
Yeah.
Arnold died.
Yeah,
Okay.
about 14 years.
It's been a long time.
Yeah.
I would imagine so. All right. So guys, what is the relevance of all this game to now? Yeah. So guys, 2 facts. So let us recapitulate the 2 facts we learned. First of all, 3 facts we learned. There is the universal approximation, which gives us confidence in the standard perceptron. right? That using a network of perceptron, we can approximate any function. In practice, you don't do single layer, you do multi-layer because it's more efficient. One way of putting it, a practical way of putting it. A different way of putting it is that you learn higher and higher order or representation as you go deeper and deeper into the network. So you systematically learn. Now, the only trouble is it doesn't exactly tell you how it learned, what it learned. It just says, I'll give you perfect predictions or very good predictions. Don't ask me how. Right? Then comes the splines. We talked about splines. The basic intuition you should carry is splines are curves that ultimately try to have minimized curvature energy, bending energy, but still try to honor or go proximal to all the points. Yeah. And splines can come in all sorts of shapes and varieties. B-splines are very popular. And typically when people do B-splines, so now it gets a little bit mathsy. You can do it in a constraint. It has a basis. You can expand it in basis functions and I won't go into that, but the most popular basis people always take is 3. Natural cubic splines and third order B-splines are the most popular thing. This paper in particular takes a third order B-spline. Now, and then the last point is a Kolmogorov-Arnold theorem, which is essentially this little game that I played with you guys was showing that any function, a multivariate function, in this case of 2 variables, you can somehow represent it, separate it out as univariate functions and do their additions, and then possibly yet another function on top of it, or a bunch of functions on top of it, right? So that is the Ka representation theorem. Now notice that I glossed over one fact, which I'll now dwell upon. If you look now, with that fact, let us start reading the paper. This paper, I'll just read the summary and then I'll explain the intuition. By the way, this paper is written, is a mix of physicists in them. You can imagine they're very excited about it. It has come from some pretty prestigious research powerhouses. As you can see, you have MIT, Caltech, Northeastern. Oh, by the way, in physics, these are all big guys, and in AI, these are again very big guys. And SF Institute for AI and Fundamental Interactions. It says, inspired by the Kolmogorov-Arnold representation theorem, we propose CAN as promising alternatives to MLP. While MLPs have fixed activations on nodes, CANs have learnable activation functions on edges. So this was the intuition I was talking about, turning it upside down. Right? CANs have no linear weights at all. Every weight parameter is replaced by a univariate function. And what does the node do? It just adds them up. It's a very trivial linear. The linear operation is very trivial. The only thing allowed is addition. Right? And a weight is replaced by a univariate function parameterized as a spline. So the question is, why splines? Well, one simple reason is people in engineering have used splines a lot. They know its good properties, that it has local behavior and so on and so forth. The numerical toolings exist for splines to use. So the researchers must have used. In subsequent work that has followed this paper, there have been people who have used other functions equally good. For example, there has been downstream research using Chebyshev polynomials and Chebyshev functions. And Chebyshev polynomials form another very efficient basis for representing it. So when we use splines, we should just say that splines are a promising candidate. You could replace it with any sufficiently flexible function which has a good basis and which has at least the property that changes stay local, right? So any good thing that you can think of, you can drag it in. I would generalize it to that. Right. We show that this seemingly simple change makes CANs outperform MLP in terms of accuracy and interpretability on small scale AI plus science tasks. This statement is where I suppose there was a lot of angst expressed. Like some completely agreed with it. Some said, oh, no, not really. These guys cheated. They didn't train the MLP long enough and it would have given just as much accuracy and whatnot. I mean, I don't know. You hear about these things. But actually what they're saying is something quite simple in my view. They're saying, you know, this is a first paper. It's a proof of concept. It's opening the door to a new area of research. That's the way I would look at this paper. And that you need, and they say it later on, that a lot of subsequent work is needed. And interpretability, there is absolutely no arguing with it. It is far more interpretable. And you will see in a moment. Yeah. Why? And cans can be intuitively visualized, and they give you a visualization. Obviously, right up front, when you look at the picture, there is nothing you can make out of it. So we'll deconstruct it and break it up into pieces. They go on and they say that, for example, if you look at this function, and they, of course, deliberately have chosen a function that is highly, highly nonlinear. It is smooth, differentiable, and nonlinear. And you can imagine that if you try to approximate it with ReLUs, with its like piecewise linear little pieces, it will not approximate it so well, and it will struggle to approximate it. You will need a much bigger network, right? You clearly can see. So interesting pairs of functions. So nice when you do that. And as we will see, by the way, do you notice that this function is exactly what our Ka representation, the way we are breaking up, looks like? Like this function, let me write it as two variables. It is exp 1 over n of, let us say, sine square. Let's say if it was just x and y. Let's say if it was just two variables, and this is half, let me just say 1 over 2, two variables. Now you realize that this is literally the Ka, like from a Kolmogorov-Arnold perspective, this is lovely. This is a univariate function. This is a univariate function. Plus is the only operation we do. And after that, all you're doing is exponentiating to half of this, which is an outer function, right? So this literally fits into the very intuitive breakdown using the Ka theorem, right? But MLP sort of struggles with it now. Now, they say proposed Kolmogorov-Arnold networks are in honor of two great late mathematicians. Sorry, it says both are gone. Kolmogorov and Arnold, Vladimir Arnold. Cans are mathematically sound, accurate, and interpretable. Right? Let's just say that these two parts, mathematically sound and interpretable, I don't think anybody argues with. Accurate, you may say, well, it's accurate, but maybe MLPs could also be as accurate. Yeah. But it certainly converges. But it's one of the ironies that because of the mathematical complexity that it brings, it converges more slowly. That is its big downside. It takes more training to make it converge.
So how do we intuitively say that okay, it's interpretable? Because
you'll see why.
Okay.
So when you ask this question, why is it interpretable? You will see in a moment. Right? So what are these networks? So let me say what the theorem really says. What I will do is, and as these authors do in so many words, through matrices, through diagrams, they will just break this equation up in the language of neural networks, right? Let us convert this expression, which looks very abstract, to something very real. And we will do with two dimensions. Let's just say x1, x2, two input dimension, right? So what you're basically saying is your input space is input, x is just x1, x2. In other words, it's going from a plane to some real value, right? This is r squared, some real value. We'll just take it two dimensions just to make it simple. What this theorem is saying is that there is, let me just write this theorem down and then gradually unpack it. So it is saying f x1, x2 can be represented as functions which are a pi, let me just call it pi q summation, q functions. A q of this q is equal to 1 to 5. How many variables are there? Dimensions are there? 2. So 2 n plus 1. So in this particular case would be 5, right? So we need 5 outer functions. Those 5 outer functions can only act on, each outer function has to act on some inner function. Let's just call, they use the notation of phi, q, p, right? So here, let me just say q1, because there are two variables of x1 plus x2, 2. So two univariate functions, but there are q of them, right? q2 of them. Now, what does that mean? This it says that you're guaranteed every single mapping from R2 to a line, any function, can be represented by this weird expression. Now it still looks rather abstract, right? So let's decompose and make it pictorial. Right? What we do is, let's start with x1 and x2. There are five sets of these pies are there, right? 5 of them are there. So what we will do is, and there are 2 of these, so we will make these 2 sets, because there are 2 sets here, of 5. 1, 2, 3, 4. Let's give it a tail, 5. And another 5. 4. So let me call this 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Are we together? This.
How do you get the 5? 2n plus 1.
2n plus 1. 2n plus 1. There are 5 functions.
Assume such a function exists from R squared to R1. That's the way we go about
it. Yeah. So no, it's a construction. What the K theorem says, that if you do this, you will succeed.
Okay.
Right? You will succeed because there are 5 of these pi functions, right? So let me make this a function pi. This is the pi 1. This is pi 2 function. This is pi 3. So
here, why 5 functions?
Yes. See, Kolmogorov-Arnold says that look at the dimension. What is the input dimension? 2, right? It says that 2n plus 1. So 2 times 2 plus 1 is?
No, that
5.
I get that one, but
Why?
It looks like a magical
It does look like magic.
Yeah.
So for that, you have to get, frankly, a little bit deeper into the mathematics, right?
So right now we are assuming that, okay, they are suggesting that we are.
Yeah. No, see, what they're saying is, 1 second, guys, let me finish this. What they're saying is, you need at most 5 functions. Doesn't mean that you need 5 functions. And this is an important point. You need at most 5 outer functions. In reality, you will need more. So mathematicians always prove theorems in terms of upper bound, lower bound, so on and so forth. So what the Kolmogorov theorem says is that you can do such a decomposition needing no more than 5 functions, right? Now, why 2n plus 1? Why 2n plus 1? It gets a little bit matchy. The proof is not so something that we can cover in the space of an hour, but it is good. It's actually. But the thing is that, unfortunately, it doesn't show you the systematic process. Okay, right? So pi 4, pi 5. So we'll just draw it out. What I'm doing is making this equation drawn out in real terms. Are we together? And this will produce a result. So now let's do this. X1, let me call this phi, because this belongs to the first set. This belongs to the second set, right? Isn't it? So what I would say is, this is phi 1, 1, phi 1, 2, phi 1, phi 1, 1 and 2. Pi 1, 3, etc. So what you do here is, you take x1, it will go through 5 possible functions, right? This also goes through 5 possible functions. Why? Because if you look at it, look at this equation. For every value of q, there is a separate function that applies to x1, right? For every, because there are 5 values here. So there will be 5 different functions that will apply to like this. And likewise, you can say 2, 1, pi 2, 2, pi 2, 3. Yeah. So we'll get to that. Pi 4, 2, 5. Yeah. So we have these functions. Now what you say is that now, but look carefully, given one particular index, like a pi 1 is taking the value only from the first box, right? From this box and this box. Are we together? And it is not directly taking value. We have to first add them. So there is an additive node, right? This goes into this, and that gets fed into this, right? So your node, the so-called neural network node, right, is this box which just does the plus operation, isn't it? And the edge, what is the edge? This was the edge. Along the edge was the function, right? Along this edge is the function. And now you repeat it. Let me repeat it with a different color. This guy, another goes to this, isn't it? Are we together, guys? And now this guy and this guy go to this, and so on and so forth, right? Do I need to draw the rest? Maybe might as well, because we have so few. This, and which color is missed? Let's take some new color. What is
Pink.
missed?
Pink.
Pink. All right. Is this pink? Yes, this is pink. There we go. So this go into this. Right. And from there, so let us mark these nodes in big black colors. So you notice that the actual neural network nodes are just plus operators. And all the magic is happening on the edges.
Yes.
This value is going to the second edge, which is feeding it into the total. And this total is again just a operator, plus operator, right? And do you see that? See this equation, does it make sense? This summation, let me color it this way, color it differently. Look at this. This summation, this outer summation over 5, where is it happening? It is happening here, isn't it? Right? And the inner summation, this summation, let me color it differently. What would be a good color to pick? Sky blue, perhaps? Sky blue. Let's take sky blue. So if you look at these, this inner summation is what this first inner layer is doing. The first layer of the neural net is doing. If you look at these nodes, right? So when you represent it in a visual way, you say, oh, so this abstract, very strange equation is actually a strange kind of neural net where functions are sitting on the edge and nodes just do addition. And it takes 2 layers to make a Ka function. And a network and a function are the same thing, right? Mathematicians look at a function and they see a network and they see a function, right? So this is a function. And this network, therefore, realizes the Ka function to the extent that a Ka function can represent anything. Therefore, we can claim that this network that you are staring at will be able to realize every possible 2-dimensional function in the world that produces a scalar. Think about it. No matter how bizarre, how complicated, it will be able to solve it. Are we together?
One question, if you don't mind. Does this mean that the number of parameters in this is at most 15, or there's no such claim on that? It could be.
No, it is. It is. What you have is 5. What we did 5 times, 15. Exactly. Definitely.
So
Well, in the general case, I think there are parameters that
No.
define the splines, right?
Yes, exactly. I was going to come to that. See, guys, there are 15 functions, not 15 parameters. Right?
Okay.
There are 15 functions. Now, depends upon what you do. Now, the mysterious question is, okay, this Kolmogorov-Arnold theorem is magical, but what are those functions? Right? What do we do with the functions? Now, that is where this paper departs and goes beyond Ka theorem. It goes beyond Ka theorem in 2 specific ways. One is, it says that we will choose cubic B-splines by choice. Oh, sorry. Let me write it down. By cubic B-splines. Right? Now, a 3rd degree cubic B-spline has, I believe, 3 or 4 parameters each, right? Because it's constructive. You get the first term, then out of the first term, you construct the second term, and so on and so forth. I believe it has 3 or 4 terms. They choose this because of its flexibility. Subsequent papers have played with Chebyshev polynomials and so on and so forth, and different kinds of things, but let's stick to that. The other thing that it does is it tries to tie it to deep learning and say, and it says something quite interesting. So first, let me point out the strength and the limitations of this. Before I go into the limitations, let's try to map it to our problem, right? Let's go to the simple situation, sine x squared plus y squared. let us see if we can represent it in our network. So you have, I will convert it in the language of this network and call it x1 square and x2 square, right? So we have x1, x2. We realize that again, I'll make my 5 boxes here. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. And then you will have the 5 nodes. 1, 2, 3, 4, 5. And they will go into 5 of the pi boxes. These are the pi, and these are the 5 boxes. Pi, 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 pi. And then they will all come to 1 node. Are we together, guys? So let me just draw this together. This goes to this, and this goes to, I'm just repeating it. And the reason I'm doing it illustratively is to show you what exactly, oh, sorry, I messed up this one. This goes here, and this goes here, and oh, this one I screwed up. This goes here, and this goes here. So obviously, now think about it this way. This one, just by intuition, you can say that as it goes, you actually don't need all these functions. In this simple situation, this function is what? Quadratic function, right? Quadratic, parabolic function. Or it does a square of the number. Whatever you get, square it. Yeah. This also does exactly the same thing, quadratic. And the rest of them are just, basically they can just, for all you care, get erased. Isn't it? And what is this function? It goes in here. What is this function? This is sine, right? That is this. And so one instructive question to ask is, you can use cubic B-splines or whatever you want, but at the end of it, when you train this network, will I end up with a whole bizarre collection of functions? Look at this. It has what, 15 functions, isn't it? Will I get a very complicated, bizarre collection of functions? Or will I get something like this? That because just by human inspection, I can say, and this is a problem kids are given when you study this, okay, do a Ka decomposition of this function, and people will sit and figure it out, right? So we just did that. Or will it actually rediscover this, right? And here comes the beautiful part. When you train this neural network, what you will realize is it will come up with all of these functions, but most of the functions, their size will be so small that you can erase them. You can just zero it out. You can sort of do a reduction or a regularization and zero it out. Now, regularization here has some caveats. Just one standard L1 regularization doesn't help. You have to add some entropy terms and whatnot. So the paper has a lot of technical subtleties to it, but let's skip all of that. Let's get to the main ideas. So I'm going to state this. That process of zeroing out those functions which are actually where input and output both are small, right? Or the net outputs are very small from those functions, zeroing it out, they call it sparsification. So when you sparsify the network, this network then reduces to, simplifies to this, x1, x2 also literally should rediscover this, isn't it? And these two should then go and feed into a function, a node, a sort of a function. So this is your pi function, and these are your phi1, phi2 functions. It should just simplify to this, isn't it, guys? And the beautiful thing is it does that, but it also causes some very interesting thing. Can you look at the shape of these functions and map it to known functions, right? And therein is the magic. Remember, at one time I used to say, make friends with transcendental functions. They come in very handy. This is literally it, or all sorts of functions. If you, in your mental mind map, if you recognize functions, you can just say, suppose the shape is this. You can ask yourself, whatever this function, the spline came up with, can I replace that spline simply with this function, fx is equal to x squared at both of these places, right? And because this looks like a sine wave, can I just replace it with a sine? So it looks like this, therefore I'll replace it with this. If you can do that. And what they found is, and by the way, in their library that they released in their GitHub, which is very good, they actually give you a catalog. They even give a helper function that says, if you're clueless what it could be, ask this function and it will suggest you which special function is closest to. But guys, just think of the meaning of it. What it means is, if you get data that has actually been produced by y is equal to this, let us say that this is the ground truth. The network doesn't know. You give the network lots of data. You give it to a MLP and MLP will say, okay, I'll make good predictions for you, but don't ask me what that function is. But the value of KAN is, this network is, you see guys, that the moment you can replace it with known functions, what have you created? You have created a genuinely interpretable model, isn't it?
Yeah.
You have achieved something that has been pursued in this field for a very long time, at least in simple cases. By the way, this caveat should always be there throughout the reading of this paper. At this moment, it's a proof of concept. It's an argument for an approach. So almost all the examples are toy examples. So there is a criticism that has been raised, is that, well, this is only on toy data. Will it really work on big data? Right? I believe that it probably will, but it opens the door to new research. You wouldn't find out whether it will or will not unless you make more progress on it. Right? So this is it. So that brings about interpretability. And then what this paper did was something remarkable. It took Feynman lectures. Any of you are familiar with the famous Feynman lectures of physics? Feynman at Caltech gave this famous lectures in physics, which inspired generations of young people to go become physicists. I was one of them, right? So that book it comes in 3 volumes and it's filled with equations, narrative equations. If you open any physics books, it is it's a festival of equations, right? Figures and equations. So, well, you harvest all the equations and then you say, can the CAN network be able to reproduce those functions? And it is surprising how, even as a first paper, which just opens a door, how remarkably well it does in reproducing and guessing the functions. It does remarkably well in guessing the functions. Now you can say that there are class of functions which are a little bit harder to guess, like, for example, Bessel's harmonics and things like that. And it turns out that even there, it comes far closer to reality than MLP, much closer to inferring the structure of those functions than MLP. So that is the gist. That's a big picture of this paper, guys. Huh? The other important thing that this paper brings out, so I guess, guys, I hope I have explained in clear terms all of this math now. Well, not all of it, but the gist of what this math is, which was perhaps the opaque part of this paper.
Important aspect.
Important aspect. Awesome. Right. So this is all this paper is saying, and it is very beautifully argued. Now, the one thing that is sort of ad hoc, and they just did it. Why spline? And why, by the way, did you stick in an activation silo in there? Those are ad hoc choices. They said, why not? We'll try it out. It worked. Hey, it worked. Yeah. At this moment, they're just opening a door to an area of research. Subsequent people, as I mentioned, have changed things around. They have put Chebyshev polynomials, they have put this, they have put that. Go ahead.
Can you remind me where the SILU activation goes in this?
Oh, literally this function, each of these functions, the phi, the inner functions,
okay.
They're made up of SILU. SILU plus spline. Now, why SILU? For a particular reason, they thought, why not? And why spline? Because spline has been the old workhorse in engineering, so let's use spline, especially because it has local structure. So it catches local structure very well. Go ahead.
I'm still not pretty clear how we can finalize on the neural network architecture. We took a 2-level architecture and it perfectly fits any function that have 2 levels.
Yeah.
What if there are multiple levels? It's like an
good question. So hold that thought in your mind. I'm coming to that itself. That is the limitation of this and how they break through this. So, so guys, this is it. Huh? So splines, these are the basis functions. The B are the basis functions, and they go only up to level 3. Somewhere it mentions that they go only to level 3. But the fact that they can capture anything with level 3 with pretty good. Now you can say that, well, that's a limitation. Now KN is no more guaranteed. because you deliberately took a very rigid function and says it is enough. And the argument is very interesting, actually. People have tried apparently this approach in the past. They haven't gotten very successful. One of the reasons is the Cannes theorem is not constructive. It doesn't show you the way. So the function that you may end up with may have bizarre shape. And it may even have a fractal structure, right? And by the way, the fact that the word fractal is lurking somewhere here, again, speaks to the fact that a lot of this is very close to another work of these great mathematicians, namely the Cannes theorem, the CAM theorem, and its relationship to chaos and nonlinear dynamics and fractals and so forth. So a lot of those are very interrelated things out there, but we'll leave that. So now what they propose is this. They say that, see guys, two layers, what we will consider is this. We will open up this here to not just 5, but to arbitrary depth. Pick your depth. Don't limit it to 5, go more. And the second thing you do is, this is only one CAN layer of your network. Go deep. Like the output of this, feed it into the next layer and the next layer and the next layer. Right? So make a deep network of CANs, CAN layer. So instead of MLP layer, have layers of CAN. Are we together? Right? And what they found empirically is that the hypothesis was that, just like in feed-forward network, one single layer can solve your problem, but it is inefficient. But when you break it down into multiple layers, then it does solve the problem well, and it's nice, smooth, differentiable function. They observe that behavior here also, that when you layer up the CANs, and you sort of open the gate to being it a little bit wider, then you get very, very good networks that solve the problems, a lot of practical problems very well.
So how do we sort of like make it as like a more breadth? So let's say, for example, we are taking X1 and X2.
Yeah.
And we are going through like whether deepness is like, okay, 5 is fine. But at the end, I'm getting only one value.
No, then again put another layer. Now don't take one value. So feed this into the yet another, treat this as inputs.
Okay.
To yet another CAN, to yet another CAN.
Okay.
Yeah. And keep going forward like that.
Okay. Not sort of like breaking up the front.
That is it. We keep going there, going forward like that. So then it has. Go ahead.
So if I save an MLP network, it's just a bunch of weights and bias numbers.
Yeah.
On the disk, right? What will this be saved as?
Yeah. Prasanna's question is, if I save this network after it has been trained, in a feed-forward network, it's a set of weights and biases. What will it be here? See, because they chose a basis, namely spline, and up to 3rd degree. So it has, for each of those curves, it has 3, 4, at most 3, 4 parameters. So you're still saving weight. Those are not weights, those are numbers. Those are coefficients of the splines, of the spline functions, right? Spline basis functions.
So one more. Sorry,
Yeah.
go ahead.
And now comes the question that somebody is asking, is there a proof of backpropagation? A backpropagation proof needs just only one and one statement only, that the function should be differentiable.
Yeah.
Because you use splines, which inherently are differentiable, right? So backpropagation is guaranteed.
Okay, so that's where like my question is about the learnable.
Yeah.
So because it is differentiable, you
It
can
is
make it
learnable.
learnable.
Yes.
Could you
Another question is when we start out like the one layer, the CAN layer, the initial number of functions is essentially n multiplied by 2n minus 1, right? Is roughly
2n plus
the
1.
quadratic.
2n plus 1.
Oh, 2n plus 1. Yeah, it roughly is a quadratic. So
Yes, it is true.
yeah, so that's the versus number of connections in MLP is the same level of complexity.
I would say, yes, you're absolutely right, Tom. These networks, right, I would argue that two things happen. It is simultaneously or paradoxically more complex than MLP and less complex. What do I mean by that? If you are looking at a single layer, like you said, good heavens, if the dimensionality is D, just in the very first layer, you will be putting together, right, a 2n plus 1 times the input dimension. So you're putting in 15 boxes, in this particular case, you're putting 10 boxes together, right? 5 times 2 is 10, right? Just one layer gets you to that. Plus you would be putting yet another 5 boxes for the outer layer. So you have 15 boxes just for 2 dimensions. And each box is now not a weight, but it is a spline, right? Or subsequent work, Chebyshev or whatever, all of which have coefficients. So you have 15 times, let's say 4 or 5 coefficients, stored 60 coefficients stored, and it is very sensitive to the input dimension. That fact is definitely true, and therefore we can say, in some sense, it is more complex than MLP. Now, I also made the statement that paradoxically, it is less complex than MLP, and that goes to the heart of why CANs have proved to be more efficient. See, what they do is they quickly zero in and figure out the mathematical functions. And so the depth of the layers that you have to put together to realize something in CAN and achieve the same level of accuracy, they have empirically shown is orders of magnitude less than MLP. Literally orders of magnitude less than MLP.
Just a quick note, if you look at the top of page 7 of the paper, there's a compact statement about what you're discussing right now.
Oh, you did? Please point me to that.
At the top of
page 7. Oh, yes, absolutely. Thank you. Yeah, right here. Their total of blood. In contrast, yes. Let us read it out. Thank you for pointing this out. So let us read this lovely thing, which I sort of argued, but I hope is much more precisely here. Then there are in total of blah, n square L plus G plus, that is the order n square LG parameters with each spline. In contrast, an MLP with depth L and width only needs these many parameters, which appears to be more efficient than CAN, right? So this goes to Tom's point that look at this, we have replaced weights with functions, each with many coefficients. Good heavens, what are we up to? Fortunately, CANs usually require much smaller n than MLP. Right, so MLPs, which not only saves parameters, but also achieves better generalization and facilitates interpretability. Right, we remark, and by the way, there's something in figure 3.1 and 3.3. At this point, we should visit that for sure. We remark that for 1D problems, we take n is equal to L is equal to 1, and the CAN network in our implementation is nothing but a spline approximation. For higher dimensions, we characterize and generalize the behavior of CANs with a theorem below. So then there's more that they say, but let's go look at this figure 3.1. But okay, guys, now what I would like to do is let us study one more thing. See, you may ask that splines are there. Why do we need the CAN theorem, a KA theorem representation? A spline can, in at least one dimension, approximate any function. That's what splines are for, right? Locally piecewise smooth, right? Bend this thing and it will do it. So what's the big deal about it? The big deal is that when you go to higher dimensions, functions of higher dimensions, splines suffer from the curse of dimensionality. Why is it? Remember, the heart of it goes back to this, you know, the duck weights that I was talking about with that physical duck weights, which in more fancy splines becomes the control points. You have to pick those control points that will pull the surface in high dimensions. You realize that the number of control points exponentially grow. And it is also hard to decide where to put the control points, right? So splines suffer from the curse of dimensionality, which is why they have rarely been used for high dimensional regression. They don't, right? And so what is the contribution of the Kolmogorov-Arnold theorem? Main contribution is it says, hey, splines are fine. They work in one dimension. Now let us take every multivariate problem and make it into a univariate problem. So you solve the problem in 2 big pieces. One says, let's make every multivariate problem a univariate problem. And the second says, go use splines. Now we can use splines and you don't suffer from the curse of dimensionality. Right? And then you get the benefit as opposed to feed forward. Namely, you have locality because splines have this behavior that they're locally learning. But it also gives you one more benefit, which is shocking. So now let's look at the positives that come out of it. Right? The positives that come out of it are remarkable, and we'll talk about it. But let's go now. I would just go and visit all the images because I think we can finish the paper in terms of just the images. So guys, does this Now, does this equation make total sense to us? We are good friends with it, right? And what have we done? Look carefully. If you notice, we have said magic is in the node, is in the edges, right? Not in the nodes. Nodes are just plus operations, isn't it? As opposed to your, and if you look at this, the MLP forces you to pick a activation function in the classic sense. Or even if you make them slightly learnable, you still don't get the full flexibility in which every edge learns its own function, right? And non-linear learnable, etc., etc. This image make. Now let's see if the second image makes it. Oh, by the way, does this equation, so now you realize why this equation is literally tailor-made for this, to showcase the power of this and show how bad MLPs can be relatively. Right.
May I make a comment?
Yeah, please go ahead.
Yeah, I was just, I mean, if you go back to that diagram, I suppose, you know, these names as to what is a node and what is an edge, I mean, that's kind of arbitrary, but in a sense, I would rather call these functions the nodes. and the simple summation is just kind of a connector between those function nodes.
Yeah, you're right. I wouldn't disagree with that. So this is actually one of the things people talk about, that, hey, what you're doing is making the node into just the activations. And then, well, there are two kinds of nodes. What you're basically saying is that you're alternating between summation nodes and complex function nodes, effectively. Right? That's one way of looking at it. See, these are visual interpretations. At the end of it, what the Can theorem and the MLP, if you really go to the math, what it is saying is, and look at the structure of this carefully. Just look at it. Given the input, what are you doing? Linear transform, non-linear transform, linear transform, non-linear transform, linear transform, and so on and so forth, right? Whereas if you look at this, it is slightly, it's different. It is saying every layer is just a whole bundle of non-linear transforms of univariate summation, univariate function summations, right? So the crucial difference is in the way mathematically they manifest themselves, right? And then then you can visually sort of represent it. And the point that you make is valid. You know, you can say that, well, at the end of it, when we visualize these things with images, we are just imposing an interpretation on it. So, and so they do make this point that mathematically, Kalmogorov, so now one point that they make is, let's go over this picture. So they have written Can with this. They're saying it's the work of these two mathematicians and a network, and it becomes Can. Mathematical, you replace universal approximation theorem with Kolmogorov-Arnold theorem. Like that gives you the solid foundation for it. By the way, I must also say that when you stack cans, layers of cans, what you're doing, the way I look at it is, the inner layers are Can, outer layers are still MLP, multi-layered, right? So MLPs are not gone. You're just creating a new kind of MLP made up of cans, right? So this makes sense. Can scaling law, I'll talk about scaling law. Let me do that. Grid extensions just say that you can, you know, remember the splines, you can pick control points, and by taking more control points, you can get more accurate, right? Application data fitting, so accuracy. Interesting is partial differential equation. We'll come to that. Very interesting idea. And interpretability to me is the most, or the big thing, an application. And see, to me, right, if I were to look at this paper, its main contribution is, here are things we couldn't do with MLP, we can do with that. First of all, it gives you a simplified picture. Physicists always search for the simplest mathematical explanation of a phenomenon. This network helps you discover or collaborates with you in discovering such an expression. And it is applicable to math and physics. That to me is the main contribution. Other things are all okay. It's different. Right? Now, I didn't speak of the scaling law. See, the neural scaling law says that if you have the loss function approximately goes as n to the minus alpha, or 1 over n to the alpha. N is the number of parameters. Are we together? Right. and this alpha parameter. Now the thing is that n is your number of, I think it's the dimensions of the number of complexity of the models. I keep forgetting it. That's silly. I shouldn't forget that. Where is the scaling law thing gone? It's in here. And scaling law, okay. So the point they make, where is n? Yeah, a phenomena test decreases with model parameters. Yeah, n is the number of model parameters. Yeah, that makes sense. It has to be the model parameters. So if you have, if you can build a network with lesser parameters, right, you will get, generally believed that smaller the model, the less the loss, right? Loss is a measure of how wrong it is. So the bigger the model, the less wrong it will be. We have observed the scaling law. But crucially, there is this factor, which is alpha. Now, what happens with MLP is this alpha, or all other networks, they go in and there's a table somewhere that shows that all of these alphas, they sort of somehow suffer from the curse of dimensionality.
So the alpha is the learning rate, right? Or...
Yeah, in a way, loss. Yeah, like how fast the network learns as you grow the network. Loss decreases as you grow the network. Take bigger and bigger networks into place. And so one of the visualizations that's very nice is, okay, forget this one. Where is this? Grids. No, this is about grid size and steps and so forth. I'll skip this figure. This figure is interesting, but let me go to the scaling law because to finish the thought. Yeah, look at this. What it says is that for reasons that become clear in the mathematics, the scaling law alpha for CAN is comes out to be, let's say, 4 for a particular case. Which case did it take? Alpha is, yeah. So in the case of CANs, it is alpha is equal to 4 when you work out the theory. It is independent of the dimensionality and so on and so forth, the depth of the neural network and so forth. So this is the theoretical. Let me highlight this picture very big. Why am I not able to? Oops, what just happened? Okay. Did I completely miss? Apologize. No, much later. Maybe I can decrease it a bit. And we'll come back to that lovely picture in a moment. Yeah, look at this. So if you guys pay attention to, let me do this. Do you see that this is a theoretical n to the -4? Right. Now observe that the CAN is deep blue. It is this line. Do you see this? So as you increase the number of parameters, the test root mean squared error, a measure of loss, rapidly decreases, isn't it? So what it means is that it's more efficient as you grow the network, which is why I made that statement, which was that CANs are in some sense more complex, but in another sense, much simpler than MLP, because the loss falls very rapidly as you scale the CAN. It doesn't fall. Actually, if you look at the MLPs, you look at the MLPs here, they don't actually come down, they saturate after a little while. And they go on showing it. They just go on showing it for different functions, Bessel's functions, this function, this function, this function, many, many different functions. They show that no matter what, these things are more efficient than that. Are we together? And now I'll go back to this is a Bessel function. J0 is a Bessel function, the first harmonic. Why are Bessel's functions important? Well, if you do quantum physics or any kind of physics, they permeate all of physics. They keep popping up in the explanations of nature all over the place. So there is one picture that I would like to explain, which is the process, which they recommend that people follow. Yeah, this picture. So what they say is that, let's say that you have two inputs, X and Y. Let us say that you happen to know that the ground truth is this. This is the actual ground truth. But the machine doesn't know, right? So what you will do is, you will train the machine And this is what you get. So you notice that there are two dark lines. They actually just, this is a dark line here. This is a darkish line, somewhat dark line, and dark line. All other lines, do you notice, are faint, right? So when you sparsify that, you prune that, when you regularize it, you end up with this guy. This makes sense? Yeah. When you come to this guy, then what you do is you eyeball it. You eyeball each one of it. So first you eyeball this guy. What does it look to you guys? If you were to just look at it, you would say, what? It looks to me like a square function, quadratic function, right? So you say, okay, I'm going to replace, well, in this diagram, they started with the left one first. So what does the left one look to you like? A sine wave, right? So, something like a sine. So you replace it with that. Then you go and replace the other one with that. So you can say that, let me just start putting guesses here. You say sine, square, and this looks like e to the x, something like that, right? Something like that. So you do those substitutions. So you come here. What you have done, but the problem is they will still have affine parameters, because what you are basically saying is sine of, let's say, sine of, you can say sine of x, but that still leaves a parameter possible, some proportion of x, a, isn't it? And then you're adding x square, but x square, which is y square, let's say this is y and this was x. So this is y square, but that also leaves the possibility of some constant b, isn't it? Then it is feeding into the top box here, and that is an exponentiation. So that is e, but if you do e, then it again leaves the possibility of yet another constant, right, to get the output, some proportionality. So all you need to do is, once you have guessed, further train the model and figure out, that is simply an exercise in linear regression, isn't it? Finding out three affine parameters, three constants, right? And do that. And therefore, what have you done? You have, do you notice that you have just reconstructed or rediscovered it? And by the way, if you happen to see a number that looks suspicious, like 3.141, 3.14, that should give you an immediate suspicion it is pi, right? And so this is the remarkable thing I found about this paper, that you can essentially rediscover the ground truth as a function, not just, okay, I have a relationship, I can make good predictions. This is what an MLP doesn't do and can do. And to me, if you were to ask, what is the real value of this paper, of this discovery? I think it is this, that you can come up with a representation, explainable mathematical representation for given data of input output. Now, again, with the caveats, it works with toy examples, with the things that they mention in this paper. Everywhere they keep saying it's toy data set, toy data set. And it is true. At this moment, this paper opens the door to this kind of inquiry. Whether or not it really works for very, very complex high-dimensional situation, I think further research will show, but it's certainly a promising direction to pursue. Right? So in scaling law, you can see, so the graph after graph, I won't go into that, but important thing is that if you look at the errors, look at this column, you notice that the best can test RMSE, when you compare it with shapes, like how many networks, one of the interesting thing that it comes out with is that it has a very low root mean squared error. 10 to the -5, -4, etc. The results are pretty good, right? And interestingly, sometimes, people are told, okay, here's a function. Try to break it up into into the Ka representation. So we all will try and do something. It may be right, but generally this network, because see, the theorem doesn't tell you what functions those are. The good thing is that with this network, you can actually rediscover or get a better sense of those functions. It also behaves very well with special functions like the Bessel's functions, etc. More interestingly, it shows you the internal structure in some sense to understand those functions. They take this example of u plus v, 1 plus uv, right, as an example, and show how you can play around with that, how the losses go, right? As you can see, if you're trying to solve partial differential equation, by the way, these days, there's a huge emphasis on using neural networks with partial differential equations and so forth. When you look at that, that is where, in the domain of science, that is where CANs begin to shine, because look at the loss function for MLP, right? It's pretty much resisting any learning out there. Relatively speaking, look at the way the like CAN has learned of the same size. A CAN, do you notice a CAN of that size is this? But you can say, well, you know, you took, it's not apples to apples comparison. You need to take a much bigger MLP. But how much bigger? See, look at this. This, how much bigger it is. It is orders of magnitude bigger, right? And when you think of 100, 100, 100, you realize that you're talking of 10,000 plus 10,000 weights sitting in between. So a lot of things going in there. So that speaks to the fact that it takes a much more complex MLP network to solve this problem. The other point, which goes to catastrophic forgetting, a very interesting thing they did. And this goes to what we do with fine tuning, right? See, suppose you train the model with just this data in the beginning, in phase one. And then what you do is after, so you give data that is just this, the first Gaussian. And then you give it data that looks like this. And then you give it data that looks like this. Think of it them as fine-tuning, continuous training, right? What is it doing? Look at what MLP does. You give it the first one, it comes up with something like this. You would expect it to do that, right? In the regime of the data, see, what is the regime of the data? This is the regime of the data. Both of them are doing equally well, or they're both doing well, isn't it? Then what happens? When you give the second data, this MLP, what it does, it begins to do well in the regime of the new data. But what happens here?
Totally forget.
It completely forgets that. So it keeps chasing the structure, like it overfits to the new data, essentially, continually, right? Keeps chasing the structure only of the new data. But what CAN is doing is, look at this. It is layering it on top. It's saying that is there and this is there because I haven't found evidence to negate the previous. In that regime, whatever it is, that learning is not wiped out, right? And if you think in terms of the CAN structure, if you were to just think in terms of this, why is this happening? I would hazard a guess that the reason is that you see this sparsification here, those other boxes are still there. You give a different regime of data, they begin to light up and take over the responsibility of that regime of data, right? Without sacrificing the previous regime of data.
Wouldn't it change the values in the already learned data?
No, that's the whole point. It doesn't.
Yeah, it's effectively decomposing.
It effectively decomposes. Yes, exactly. See, remember, it's a linear decomposition, right? That's the whole beauty of the CAN. That see, if this, like these functions are there, they're additive. And if each addresses a different regime of the data, but is zero everywhere else, right? Then for a situation like this, it would really work beautifully.
Right. May I make a comment?
Yeah, sure, please.
You know, it's often heard sort of colloquially that forgetting is actually a very important element of sort of, you know, remaining sane as human beings, right? And I imagine the same thing may exist for these models. If all we can do is sort of add to the space without removing information which we've now learned is invalid or bad. I wonder, you know, what work is going to come down the road in this CAN field to actually help the models sort of unlearn, you know, past data. And is there any? Do you know of any analog for that in the MLP space?
Right. See, Andrew, that's a very good comment. See, the whole essence of learning is to look at facts, generalize from that to a concept, and then there is no use of those facts. You can forget those facts because you have a model from which you can derive the facts effectively. So forgetting is certainly at the core of it. And obviously psychologists will tell you that people who don't forget anything in their life live pretty tough lives. So forgetting is part of learning. The whole point of learning is so that you don't have to remember. It's true. Now, when it comes to practical consideration, there are situations where you want to forget and situations you don't want to forget. So here is a thing. Suppose the data really has changed. Like, for example, weather patterns have changed. Right? Today, it is a fact that almost all the weather models are obsolete. Have you noticed that? The joke is if the weather prediction says it's going to rain, wear your shorts and go jog. Right? It used to not happen. Weather predictions were very accurate, but recently weather has changed so much that in many areas it's become rather unpredictable. Right? We need new models. So there is a certain degree of forgetfulness that is necessary because it is a displacement. This fact is in the same regime, same geographical location, but it is showing entirely different behavior. So here forgetting is useful, but at some places it's additive. Like, for example, if you look at this situation, data, if you look at this is deliberately an additive process. You're saying that I'm giving you different data for different parts of the input space, regimes of the input space separately, and one does not displace the other. In fact, this is a disjoint intersection. Right? This is this disjoint partitioning of the input space, and then I'm giving you the data. And here the context is don't forget. Just because I'm giving you a different data, don't forget to. So it's, in other words, it's an additive process. So the question is, what is your context? What do you want to do? Like, for example, in CAN also, suppose the second piece of data was, let me just say, the first piece of data was like this and silent. And the second piece of data was not just this, but it was also like this. So what would it do to this? It would force it to unlearn some of that behavior, right? But it just so happens that in the example they show, they are trying to give you disjoint regimes of the data. Right? And the good thing is, and this is a remarkable thing, as far as I know, this is remarkable because it is the first time I'm seeing something that you don't worry about catastrophic forgetting if you really do that. Now, whether it is really practical in large language models, for example, when you give a new data for fine-tuning, it is slightly different from the data it has been trained on. Otherwise, there's no point in giving it the data to fine-tune. But it is not that different. It has overlap with the previous data. And so is the story equally clean and beautiful there? I don't know. Most probably, in such real life situation, there will be some forgetting and there will be some learning. That's
moreover, like they claim that okay, it is working for mathematical problem and the physics problem.
Yeah.
So the data is not going to change, or maybe
realities don't change.
Reality is going to be the same.
Yeah. Right? But I think the forgetting here is important. Like there's no distillation of learning.
Correct.
What they're claiming is that when you're getting a new data, so with the traditional MLP, there will be distillation and more waiting for the new data.
Correct.
Here, since it is not there.
All right.
And it is up to your use case whether you want to kind of like delete that or not.
Okay. So guys, I'll move fast. We are way beyond the time. So let me just finish it and we'll have the discussions. The knot theory is something. Go ahead. Go ahead. Somebody is saying something.
Asif, there's one question in the chat actually, if you want to cover that. In these toy examples, how is the simulated data generated?
That actually you have to look at it. I think at this moment they're just sampling off the functions directly. I don't think they are at this moment injecting noise, or maybe they're injecting a little bit of Gaussian noise. I didn't look into the details very carefully.
To generate the data, just
a sample.
Yeah, just a function, right? So you write a function.
Yeah. I mean, it's an exercise in reverse engineering. That's why they don't care.
Okay, guys, so let's continue. I know that we have a lot of discussion, but we are way above the hour, so I'll finish it. Knot theory is very interesting. To know whether two knots are equivalent, like one can be deformed into another, is not just a fun pastime for mathematicians. It has deep implications. For example, one of the things that I was working on, there are these models called SCRM models. They're supposed to be topologically stable in some sense or not, or stable structures in quantum fields. But anyway, that's a separate thing. Knot theory and its associated areas, topology and etc., topological solitons and things like that are very interesting. So it has something to say there. The interesting thing is that it can help you rediscover some of the mathematics. For example, phase transition equation, it sort of co-discovers it. So the argument these people make is that, hey, here is a tool to help a scientist essentially co-discover the mathematical relationships. And these relationships are not easy relationships. Like you and I wouldn't normally think of these relationships so easily. And the fact that it can do that, more than the fact that it's better than MLP or worse than MLP and so on and so forth, and those things the future will determine. But it is very clear that for scientists, this looks like a very useful tool for co-discovery. And I think that is its main value. And I would like to stop with that. So those of you who are physically inclined may want to delve deeper into it. There's some interesting tidbits. There's this diagram, which I don't think it states the obvious.
Very good candidate for the physics-inspired neural network, right?
But that is true. And one more thing I would say here. So,
may I reiterate my prior question a little more clearly?
Sure.
Is there an analogous mode in, well, maybe not analogous, but is there any known mode in MLP training to specifically forget some datum? I guess maybe you feed back a part of the training set, but you use an inverse learning function. I mean, would that be a way to sort of,
Right.
let's say you discover at some future point that part of your data set was just completely wrong. What do you do?
So, Andrew, I do know that that's an active area of research. In fact, last year or some point, one of the key areas that researchers thought was a hard problem was how to consciously make it forget data. This has a lot of implications. For example, GDPR, right? In Europe, you have a right to be forgotten and your data. We'll come to questions.
No, but this has to do
Okay, go ahead.
this. It actually depends like a lot on the loss function that you use and like the data points that you're looking at, and then also the structure of like the neural network that you have. Because like for like really like a really simple case, like if you're looking at like a simple neural network, regardless of how deep it is, but with no convolutions and like no recursion, and then also you're taking like stochastic gradient descent, like a really basic like loss function, then you can do this because like the losses are basically like additive of course. You can basically like swap any training data for any training data. But this is not true like when you start going into like more complex loss functions, or if you start adding like recursions and stuff like that.
That's
so.
All right. So Yashida here mentioned that it's a little bit of a function of how complex networks you have and what your loss function is. Very true. Thank you for that feedback. And guys, this is a very big area of research. There are tons of research paper on how to consciously and non-destructively make it forget things so that if it forgets this, it doesn't forget a lot of other useful things. Very active area of research that can be gone into. What implications CAN has there, I don't know. I think it's a bit early to tell, Andrew. And also, frankly, that forgetting a bit of research, I am not an expert in, so I don't feel qualified to speak on that.
Thank you for that. Yeah, it's an interesting topic.
Yes.
They also use sparse autoencoders to figure out like which part of the video.
Yes, that's right. Yeah. In fact, if you remember the last paper that we did, from
exactly.
We got into that. We got into the sparse autoencoders to extract the features. And what you can do is go suppress the feature. Andrew, this is a good comment. See, last week we did the paper, if you remember, on the features that the machine is learning, like psychopancy or the Golden Gate and things like that. And once you discover the feature, if you remember in that paper, we talked about the fact that you can either amplify or suppress that feature.
Right? Yeah, unfortunately, this is the first meeting for me, so I was not present last week, but I think I know the paper you're talking about, so I'll go take a look.
Yeah, in that case, Andrew, a warm welcome to our small learning community.
And you can watch that YouTube video. It is recorded.
All right.
If someone could post that to the chat, I'd be grateful. Thank you.
Okay, I'll do that. If you can just look at the YouTube video and post it to our Discord.
Yeah.
That will be nice. Okay, guys. So with that, I'll stop the recorded part. I know that you guys have a lot of things to discuss. If you want to ask a question while the recording is still on, please do ask. Otherwise, I'm about to stop the recording.
I think like an interesting thing